Excellent.
All right, the next paper, Reliable Actors with Retry Orchestration from IBM Research. Olivier, Tardieu, Dave Grove, Gheorghe-Teodor, Bercea, Paul Castro, Jaroslaw, Cwiklik.
Good question. Jerry. We call him Jerry.
Edward Epstein. And Dave will give the talk.
All right, great. So thank you. My name is Dave Grove, and I'm here to talk about some work we did jointly with my colleagues at IBM Research, who Colleen read the names, so I don't have to. And the general area we're working on is programming models to help people build fault-tolerant applications in the cloud. More specifically, we're looking at a class of applications that aren't particularly well served by existing systems for building fault-tolerant applications. And these applications have several characteristics that make them challenging. We're interested in applications that are built using multiple third-party services by putting them together. These have heterogeneous APIs and service levels agreements. The applications often are built by combining multiple external stateful components. And an important piece of the state of the application is the progress of cross-component workflows. And these workflows may have side effects. So what happens when there's a fault? Well, when there's a fault, some tasks are going to fail, and there's a partial loss of the transient state of the application. And to be resilient, for resiliency, what we want the system to do is to automatically identify the failed task, restore some of the application state, and retry those failed tasks. And the key idea of our work, if you remember nothing else from this talk, is this concept of retry orchestration. And so we're going to have to retry tasks. And what we want the system to do is to constrain the order in which those tasks are retried to make it easier for the programmer to reason about the behavior of their application across the failures. And we want to prevent spurious retries, and we want to preserve dependencies between the tasks. So in the talk today, I'm just going to touch on various pieces of the paper to try to get a sense of what we did, and maybe intrigue you into actually reading the paper. So I'm going to talk about the programming model, a little bit about the formal semantics, dive deeper into fault tolerance, and then show some of the experiments we did. Okay, so the programming model. So we build on top of an actor programming model, which is a fairly standard thing to do in this world. Actors give you a way of encapsulating little pieces of the state of the application. You can think of an actor as an object in a partitioned global heap. So it encapsulates some piece of the state, and it exposes methods. And actors interact with each other by sending messages back and forth, which invoke these methods. These actors are globally addressable, so you don't have to be running on the same process as another actor to be able to send it a message. We're in a world of virtual actors, which is what the Orleans system coined this system, where the system manages the life cycle of the actors. So if an actor instance is needed, the system automatically places it onto an appropriate runtime process, makes sure messages will be routed to it, activates it, which means loading its in-memory state out of a stable, persistent actor store, making sure the messages go there, and eventually, if the actor becomes idle, deactivating it, so getting it out of memory to make room for other actors. And actors provide us a concurrency control system, so within an actor, there's only a single thread of execution ever active at a time, and that's an easy way, that's a good primitive to help programmers program. So we're going to go beyond actor systems in two ways. I'm just going to highlight those two pieces of the program model. So first is most actor systems really rely on asynchronous messages. So the programmer has to think in a message passing style of messages flowing around the system and how do I program against that. And we found that one thing that's pretty useful for a programmer is to allow a remote procedure call. So it's very convenient to be able to call another actor, wait for a result, get the result back, and then continue in the current scope with local variables and a flow of control. And so this picture on the right, throughout this talk, we're going to see some pictures like this. The shapes represent actor methods. Solid lines indicate when the method is actually executing, and dotted lines indicate when it's blocked. So here, the blue calls the purple calls the green finally computes the result, returns it to purple, which unblocks, computes some more, returns the result to blue, which unblocks and continues. And so if these are all different actors, it looks like the picture on the top, but we also want to allow reentrancy. So actors don't allow concurrent execution, but it's often convenient to be able to call back to the actor that called you. And here, this picture on the bottom is showing that, and here we want to allow this. So if the methods are part of the same call chain, same call stack, we want to allow those to continue. If they're from different call stacks, then they'll have to wait for their turn to execute. The second thing we do that goes beyond the traditional model is something we call tail calls. And this name is inspired by the tail call optimization in the compiler. In particular, if the last thing an actor method wants to do is call another actor method, it can do that with a tail call. And this allows an atomic transition between the running of one actor method and the scheduling of the next one. And one important thing here is if the actor does a tail call to itself, it retains the actor lock. So if the blue method is executing and it does a tail call to the purple method in actor A, even if there are other actor messages already waiting on A's queue, purple goes first. All right, so it jumps ahead of other actor methods, and that allows us to think about a way of doing that. If it's to a different method, so purple does a tail call to green, here green has no special priority. It has to wait for its turn to execute on B just like any other method would. And this combination of these things gives us a way to build workflows and to orchestrate workflows and lets us break complicated workflows, complicated steps into smaller steps that are easy to reason about while maintaining this concurrency. So we know that nothing changed between the blue and the purple method on actor A, so we can reason about that. And this is a picture from our paper just to give you a sense of the kind of workflows we can build. So here's a workflow that crosses across 5 different actors. Each of those rectangles represents an actor method invocation. The blue ones indicate methods that interact with external states. And so this has built a workflow sort of tailing through this with tail calls. And just give you a sense of the kinds of workflows we're able to build and their scope. Then just very briefly on the formal semantics. So we formalized the semantics of the programming model and some of the guarantees it gives. And I just want to talk about a couple quick things about what happens when we want to execute a method. So we're going to execute the method M on actor A. Well, in order to execute it, there has to be some message. So there's some message in the flow, and that message is runnable, which I'll talk about in the next slide. So the execution of this method can begin, and when that happens, a running actor is added to the program state. But importantly, the message remains in the flow. All right, so we're executing the method, but we did not take the message out of the flow. The message doesn't come out of the flow until the actor execution ends. And there, we simultaneously take out the method, the invocation method, and put in the result method into the order list of messages, and the actor state is removed. So to touch on this runnable predicate a little bit, the formal details are in the paper, but I just told you about 2 ways which we want to go beyond a standard actor programming model. So a standard actor programming model, runnable is very simple. A method is runnable when it's at the front of the message queue for an actor instance. With reentrancy, we have to support this priority jumping. With reentrancy, we have to support noticing when the method's part of the same call stack and letting it go. Tail calls require this priority jump to happen. And finally, this retry orchestration, which I'm going to talk about next, is what happens if you have a caller and a callee and the caller fails. Well, we'd like to delay the execution of the callee, the retry of the caller until the callee completes. And that's also captured in the semantics. This is one of the key contributions to the paper, is thinking about these various scenarios and thinking about how to exactly to formalize them so we can reason about the properties we get. So what do we do? What do we talk a little bit more about fault tolerance? So to recover from failures, the first thing we have to be able to do is we actually have to be able to detect the failures. Once we detect the failures, we can replace failed actors, retry failed tasks, and our system is going to do all of that automatically. So this requires no programmer intervention at all. However, there's still more work to do. In particular, the programmer has to plan for failures. And here the programming model's goal is to facilitate that, to make it easier for the programmer to do that. We require some programmer intervention in 2 cases. One of those is actually to plan to persist the state of the actor so it can be restored later. And the second one is when writing your actor methods, you have to think about the fact these methods will be retried on failures to try to make them retry safe. And the key thing that a programming model gives to make that easier is this thing we call retry orchestration. So when you're thinking about writing your actor methods and thinking about the fact that may be retried, the system provides you 3 main guarantees. First of all, we know which tasks have completed, and we're never going to retry those. That seems quite sensible. Secondly, we're going to preserve if an actor message queue, its in-memory queue is lost and we're restored from the persistent messages, we're going to preserve the logical order of those messages, accounting for tail calls and reentrancy. And finally, we're going to observe that happens before across failures. This is an important thing because we don't want to allow a retry of a message to be happening at the same time some previous version of itself, some callee that it called is still executing. This sort of mixes the past and the present in a way that's kind of confusing for the programmer to reason about. So we want to prevent that from happening. And just to show you some pictures of this, first for the tail call case, this is relatively simple. So in these pictures, the red blobs represent a failure. And so in the case of the tail call, really only 2 things can happen. Well, 3 things. A, there's no failure. That's the top picture. B, there's a failure and the blue method is running. Then we just retry the blue method and then we do the purple method. Or the blue method could have completed and the purple method could have failed, in which case you retry the purple method. But there's never any ambiguity here. We'll never actually retry both of those methods because we know which one of them is executing. The second is with call stacks. And so here, situations on the left, we're showing a sort of non-failed call. The caller may fail before it actually makes the call, in which case it's just a normal, we just retry the caller, it makes the call to the purple method, and so on. The callee may fail, and here we can retry the callee task, and the result gets returned to the caller task. The caller task is completely oblivious. It doesn't even know a failure happened. It was waiting for a response, it got one. Great. And the situations on the left show what happens when the caller fails while the callee is executing. And the first one of these, just the callee fails. Sorry, the caller fails, we delay the retry until the callee completes. That's indicated by the dashed red line, and then we do that. Both actors may actually be running on the same process. They might have both failed, and here we want to, we're going to have to retry both tasks, but we're going to want to schedule them so that the callee retry happens before the caller retry. And picture 5 shows an optional cancellation factor option where the system knows both if the callee is the callee of a failed caller, we can elide the retry and just go directly to the retry of the caller. So hopefully they give you some intuition. Now what's this good for? So this is 2 blobs of eligible code. The one on the left is from an old version of our system when we had much weaker retry guarantees, and the one on the right is from the current version of the system with retry orchestration. I just want to show you a couple things here. So first of all, there's some business logic. This is the code the programmer actually wanted to write, and it's basically identical in both systems. So that actually does the work of the actor method. Then you have to figure out what to do next. That's a similar amount of code in both of them. All right? But then there's all the rest of this stuff. And this is the stuff that the retry orchestration gets rid of. This is all the custom logic the programmer had to write specific to this particular actor method to detect it was being re-executed under weaker ordering semantics and deal with that mess. All right. So just quickly about our implementation choices. We built our system on top of Apache Kafka. And we have one Kafka queue per application process. And each one of the steps in our semantics just involves putting one message into one queue. And so that means we can do this without any coordination, no transaction. So in normal execution, the system is quite fast. We leverage Kafka's heartbeat mechanism for fault detection because each of our application process is attached to a Kafka group. And so we can leverage that. And where we have to do something quite a bit more expensive is in fault recovery. And so here we leverage some Kafka mechanisms. So when there's a consensus that happens and Kafka tells us there's a failure and it determines what set of processes are still alive, we then go and catalog all the recent messages to rebuild these logical callee-caller chains, the call stacks, look at the method metadata, find methods that actually had to be requeued places, figure out where we're going to put the new actor instances, put these messages into the appropriate queue, and then finally continue. All right, and this design is based on the assumption that failures are relatively infrequent, but when they happen, we have to do the right thing. So I'm going to talk just a little bit about the experimental evaluation we did. And our experiments really have 2 things we're trying to answer. First of all, does the system work? It's fairly complicated. It's supposed to be fault tolerant. Is it actually fault tolerant? And secondly, how well does it perform, both during failure-free operations? For those results, I'm going to refer you to the paper, and when failures actually happen. All right, so to do these fault tolerance experiments, we use the container shipping application. We built this as a showcase of our programming model. It's about 5,000 lines of Java-based actor code. The workflow that I showed you the picture of 10 minutes ago is a workflow from this application. So that's the kinds of things this application is doing, workflows that span across a bunch of actors. We used K3D to create a virtual multi-node Kubernetes cluster. And then since we have this virtual cluster, we can then externally, in a controlled fashion, inject faults into it. So these faults show up as sudden restarts of one of the virtual worker nodes. These restarts take out multiple application processes without any warning. And we also looked at cases of clustered failure. So when a failure happens while we're still doing failure recovery, does the system still work? What if multiple failures happen at the same time, and so on? And the key result from this is we did thousands and thousands of these failures, and the application always continued running correctly across all of these failures, kept on computing the results. So that was the main result we wanted. We're also interested in the performance. So these graphs here show performance from 2 perspectives. So the graph on the left is showing you 1,000 failures from the perspective of the runtime system. And I told you we basically have to detect the failure, we have to decide who's still alive, and then we have to do this reconciliation process. And the 3 colors on the left basically indicate that. So Kafka takes on about 9 seconds to do the heartbeat detection protocol and notice someone's dead. It takes about 2.5 seconds to figure out who's still alive. And then it takes us about 10.5 seconds to do our reconciliation and get things ready to go again. So the overall outage is about 22 seconds. The graph on the right is showing this from the application's perspective. So that order workflow I showed you before, Outside of failures, it runs in about 100 milliseconds is its typical latency. When there's a failure, the average order latency spikes to about 24 seconds. So the the outage time from the runtime's perspective is 22 seconds. From the application is 24 seconds. That seems it's basically in the same ballpark. It does take the application a little more time once it sort of comes back from a cold start for the JVMs to warm up, to load state out of data, and rebuild some caches and be able to continue. All right? And there's more details on both these experiments in the paper. So just to wrap up, hopefully I've given you a little bit of a flavor of our programming model with its virtual actors and augmented with some features like call stacks and tail calls. There's automatic always-on retry orchestration, which hopefully simplifies the developer's task. And we have an implementation, which is open source. There's also an artifact associated with the paper. We built on top of Kafka. And so hopefully this is interesting you enough to go look at the paper, check out our implementation, and there's quite a bit more details about the implementation and how we did it that's in the paper that I didn't have time to talk about today. And I'm happy to talk about it later on Discord or whatever. And so with that, questions?
Questions?
It's really interesting. Matthew Parkinson from Microsoft.
Mm-hmm.
It seems that by sort of blocking the actor, you might introduce deadlock. Is there some mechanism you're using to avoid that?
Right. So by blocking the actor, we can, right, there can be deadlocks. And to avoid it, we have a deadlock. Part of what we can do is we provide a dynamic deadlock detection algorithm that the programmer can run. Basically, it does either a postmortem over the message trace, or it can do it live. We have a live debugger where you can connect and see where things are blocked. The other thing we do is we default to timing out actor messages. So if you've been waiting, if a message has basically been blocked for multiple minutes, it'll, instead of blocking forever, it returns with a timeout error. And so you can control that as an application program. For example, when you're doing development, you might set the timeout relatively low so you would notice these things happened. But in general, if you're going to allow blocking, then you will get some deadlocks. And so it's a question of trying to figure out how to help people debug that. And that's what you pay for this programming model that lets you make a blocking call and get a response back. Right?
Thanks.
Yep.
Any other questions? Any questions online? No? You are probably familiar with that paper, Tailored Scale, of Jeff Dean and Luis Barroso, where they did a whole bunch of tricks to hide latency, like hedging requests and tying requests together and things like this. If you were to use your system, CAR, where would you do that logic? Would you push it all in the runtime? Does the application programmer have to do something?
I'm not sure what we do, actually, to be honest. Sorry. Your question's too good, Colleen.
Sorry?
Your question's too good. I'll have to think about it more.
All right, we can talk more about it.
All right. Cool. Thank you.
Next speaker?